Hello, class. I just want to go over the last section for calculus this month that we couldn't go over in class. Go ahead and take a minute to write this down, pause it, and then unpause when you're ready to listen. But hopefully, you've unpaused it by now, and we're going to talk about modeling and optimization. So, the last section we talked about identifying generally. Let me see, they weren't exactly your notes, but let me show you what we did last time. We were talking about like trying to find minimums and maximums, if you remember, like with the second derivative or first derivative test, right? The difference this time is that we're actually going to use it for not commercial interest, but for anything outside of the context of just pure theoretical math. We could use this to our advantage. Think of like if you could theoretically make a trend, or you've kind of not mastered, but you got a good feel for the general economy in the last 10 years, right? And then you identify that it's some kind of what is it? Like cubic function, roughly a cubic function, right? It might zigzag a little bit, right? But generally, you see a trend here, right? Let's say that x was in units of time, in years, right? Years. Sorry, this is really rough. And you try to model generally, okay, let's maybe make it a little bit less rough here, but let's approximate what the business is going to do. Okay, sorry, this was supposed to be an approximation of what the actual trend looks like. Okay, if you can find out the function, you can generally make a function out of this. Okay, this is why we're kind of learning math. We're trying to learn how to manipulate functions to our benefit, right? We can do kind of anything what we want with it once we master how to manipulate functions and numbers however you like. I don't know. I might be completely wrong here in how this is, but let's say if we know that, and we generally know and understand what the concepts are behind finding the maximum minimums from the last chapter, you can ideally know when to invest money, when not to invest money. Like maybe the stock prices are really high, you probably don't want to get in when it's that high. But when stock prices or things are really low in price, investments, right, where you want to see your money grow. I don't know what this could mean, but like this is a general trend for investments in stocks and the values are really low, maybe that's when you want to strike, invest your money, and then it'll go up. Okay. And I know that sounds weird, but most people are just like, I'll just wait for it to get low. But let me be honest with you, most people kind of know when it does get low. They approximate right around this time. That's when they're like, I know when to exact my money and invest it. And they'll hire people that invest like right up to the last second when it's about to go off. Okay. Most people want to invest here, but by the time they hear about it and they invest, the money's already up here. So my basic saying is math. That's kind of a weird, crude way to explain the benefits of math financially. You can do it for anything else. Hopefully, you can go beyond the extent of just commercial interest and money and trying to profiteer and whatnot. Okay, but that's probably the easiest to exemplify in our society because we are, a society that, looks to maximize money and minimize time. Okay, so that's probably the best example that we can all understand at this point. Okay, but I like you to go beyond that, the human condition, and so forth. But anyways, um, we have uses for the first derivative, second derivative test, right? So let's go through an example of what this might look like. Okay, so let's just do some general exercises to kind of get you comfortable with using the first derivative test outside of the context of just first derivative. Find the first and derivative test to find the minimum and maximum point, right? It's got to be less robotic and more realistic. We're going to go to more organic, realistic problems that might pertain to real life, right? So find two numbers whose sum is 20 and the product is as large as possible, and it has to be non-negative. That's the condition here. No negative numbers. which makes it actually easier in some ways, right? Maybe, maybe not. Okay. Find two numbers whose sum is 20. So these two numbers have to add up to 20. They have to be non-negative. And yet when you multiply them, they have to be as large as possible. So you could do this. I think 1 and times 19, 1 and 19. If you add those up, that's 20. But then if you multiply them, then that'd be like 19. And you can go down through this whole list, okay? And this is a general example where you could do that, and it would take a little bit of time to do that. But just keep in mind these problems might be a much more complex problem. We're just starting with something simple, but remember, in the future, as these problems get really tough, you probably don't want to go through this archaic way of going 1 and 19, I think 2 and 18, if they multiply, oh my gosh, that's bigger, right? You probably don't, you want to steer away from something that's inefficient, right? The name of the game, even including what I just talked about, my whole spiel up here, is efficiency, right? So let's give you an efficient way to do this. So here's the solution. I know that, let's start on sorry, my strategy is to keep these notes in the future, but then the work is the stuff I generate in the future. I don't know if that really matters to you guys. I'm sorry. Okay, so I know that one of the numbers is x. One, like a number, like a here. One of the numbers is going to be an x value, right? The sum has to be 20. So I know this is odd, but this is the best way to do this as far as I know. The other number has to be 20 minus x, because you know if you add these two, they're going to be up to 20. And that does work out, okay? So think on that for a second, okay? And I'm going to model the product. Remember the product, we want a product between x times 20, or this number and this number, to be as big as possible, right? So let's make the product into a function or some kind of equation where we can kind of apply the first derivative test, right? It's going to be the first number times the other number, which is 20 minus x. So it's the product of two numbers. Remember, the product is as large as possible. We want to maximize this. We want to see the maximum point on this function. All right, and that looks to be pretty good, right? And then let's look at what that would look like. That'd be 20x minus x squared. Okay, great. So how do we find the maximum and minimum values of this graph or this function? So now we've boiled it down to something that we're familiar with doing, right? So if you remember, let's go back to the steps here that we kind of wrote out for the first derivative test. We're going to find the first derivative, just the first derivative of the function, find the zeros, the critical points basically, or the roots. Then we're going to see if it's positive or negative, and then we're going to build a number line and see if the slopes, derivatives around your endpoints and critical points are positive and negative, and determine if those points are going to be local or minimal, maximum, or not extrema at all. Okie dokie, so let's go ahead and do that after I get back to, sorry, I have my own set of notes up so I can follow. I have organization here. Okay, so f prime, I'm going to find the derivative of these two. That's going to be 20 minus 2x. Okay, that doesn't look very hard. Okay, let's set that equal to 0. So remember, this is step 1, this is step 2. Step 3 is to find any points, x coordinates, that give me a derivative value of 0. Okay, we're trying to find, if you remember from my talk, right, to find the minimums and maximums, we got to find where the slopes are equal to 0, right? The slopes are equal to 0. So that will be, oh, sorry, I'll subtract 20 from both sides, I guess. I'll do that. Nice save, Mr. Wee. Oh, and that's minus, or it's negative 2. So let's divide both sides by negative 2. And I got 10 is a potential minimum or maximum value. I don't know. So 3 is, you build that number line and you look at 10. And if you remember, there's something that we didn't encounter in the last section with my examples, but look very carefully here. I said find the zeros for your derivatives and one other thing, your endpoints, if you have any. this function looks to go on forever and ever. Like I could continue this even if I plug in negative numbers. I don't know if it looks like this, but it could continue from left to right, correct? Right? But let's look at the original problem that we have. Find two numbers whose sum is 20 and the product is as large as possible. So I'm going to give you a hint. There are actual endpoints to this problem. What two values or what numbers can we not have? I'm going to say you can't have 0. So that's an endpoint. You can't have anything less than 0 because it can't be a negative number, right? And because we can't have a negative number, right? We can't have a negative number. I know this might be confusing, but think about it. The sum of these two numbers has to be 20. If you can't have a negative number, right? Can you have a number that's greater than 20? Think about it. If I said, okay, find two numbers whose sum is 20. Okay, one of my numbers is 21 and -1. Okay, well, that can't work because I told you that you can't have a non-negative number. So what else can go with 21? A number that is slightly bigger than 20 to give me a sum of 20. Nothing else. I can't think of any other number that's not negative, right? So that means the other number has to be, or it can't be 20. So those are actual endpoints. I can't have anything bigger than 20 and I can't have anything less than 0. So those end up being my endpoints. So just kind of FYI, we want to stick between numbers that range from 0 to 20 when we're kind of doing this number line. So keep that in mind. So that's where the endpoints are really important. Okay, now if you remember now, we just apply the first derivative. So let's pick a number between 0 and 10. I'm going to go easy. I'm just going to say that x equals 1. I'm going to test a point here. And x from 10 to 20, I'm going to pick, I don't know, I think an easy number in my head would be like something even. I like even numbers, and that's not much bigger than 10. Okay, so let's stick that into the first derivative and see if it's a positive or negative value. The first derivative is 20 minus 2 times x, or 2 times 1 in this case. So let's plug in 1 there and see what we get. So I get, that is a positive number. So that looks good. Okay, how about over here? Let's plug in 12 into the equation. That's 20 minus 2 times 12. That's going to be 20 minus 24. That gives me -4. That is a negative number. So that should tell me all the numbers from 10 to 20 are going to be negative. Okay, so what type of problem or what type of point is 10 going to be? What kind of extreme point is that going to be? We were taught that if you have something going from a positive slope, so let's pretend that this is my xy thing here, and then I say from, whoops, I kind of did it wrong, but let's just say the x-coordinate here is 10, okay, like this is saying. It has a bunch of positive slopes, evens out, so this is where the slope is 0, and then I have a bunch of negative slopes. What kind of point do we have there? We have a, sorry, that is incorrect though, but the way I drew that, but the point is correct. This is a local maximum, local max. This is a local max, which tells me that, let's see. So we can say x equals 10 is the local max. Doesn't really matter. You didn't have to do this, but the one thing that you should say now is that the numbers have to be, so if you remember, one of the numbers is x, and one of the other numbers is 20 minus x. So x equals 10, and the other number is 20 minus x, which is 10. So the two numbers we're looking at, you don't have to write it in a sentence, but the two numbers are 10. Both of them are 10. Okay, so those are two numbers whose sum is 20, but the product is as large as we can get. Okay, so think about that for a second. Rewind back if you need, but we're going to move on. Okay, so I'm going to move on. Let's see, I'm going to put this kind of guy away here. I got about 3 more problems, or 2 more problems, 2 more types of problems that we're going to look at. So in class, if we would have done this in class, I would have given you a more tough example. So let's try this, try a similar problem. And actually, you could pause and try this on your own. I mean, doing stuff on your own and letting your brain kind of critically think about what the heck is going on, um, that will actually lead to better learning. Okay, so find two numbers, non-negative. Again, whose sum is 20. But find the numbers if the sum of, and we're looking for sorry, the maximum numbers, like the biggest numbers you can get, if the sum of their squares, so this is a harder one, is as large, so it's the sum of their squares is as large as possible. So let's see what this means. We have two numbers again, whose sum is, so we have two numbers again, whose sum is 20. So how we would represent that is x and 20 minus x, okay? But let's take a look. Whose sum is 20, but find the max numbers if the sum of their squares is as large as possible. So their squares mean this. This number squared would be x squared. And this one here would be 20 minus x squared. And they're asking for the sum. So you just modeled this condition here. So find the two numbers, two biggest numbers basically, whose sum is 20. That's these two numbers. Find the max numbers if their sum of their squares is as large as possible. Okay, sorry. So just find the numbers. Sorry. So that didn't make sense. Find the numbers if the sum of their squares is as large as possible. So the sum of their squares. These are their squares, x squared and 20 minus x, and then find the sum. Okay, so now the first step, if you remember, is to find the first derivative, which is 2x plus. So you can do this in many ways, okay? You can write this out to be like, oh, I find that if I did FOIL, it would be like, let's see, 400. I'm just doing this in my head, minus, like this. I'm sorry. So you do first, or however you want to do it. First is 20 times 20, which is 400. Next one is outside, 20 times minus x. That's minus 20x. Inside is minus 20x. And then last is, what is it? Oh, is it? Oh, last is these two is minus x squared. And then you get 400 minus 40x minus x squared. Okay, and then you can find the first derivative of that. What I like to do is this here. I like to just use the power rule, or where you just put down the 2 in the front. Keep that to the first power 1, and then you take the derivative of the inside function, which is just 1. And that makes it a lot easier for me. So I think this is just 40 minus x. And if you found the, let's see, oh, minus 2x, I do apologize. So if you did the derivative of 400 minus 40x minus x squared, that would have been 0. The derivative of 400 is 0. The derivative is minus 40x is just minus 40. Wait, did I do that right? Let's see. Yeah, I think I did something wrong here. Okay, let's see what I did. Minus 20x. Huh. Oh, that's super odd. Give me 1 second, guys. Maybe you guys can kind of think along with me while I'm seeing something odd here. The thing that I'm finding odd is that if I do FOIL, I have 20 minus x times 20 minus x. This should be minus 20x. And outside should be minus 20x as well. So that gives me 400 minus 40x. Let me see. I'm going to look to my notes really quick if I did something wrong here. Oh, I see. Okay, and then minus 4x. So be very careful. The derivative of the inside function, remember I did the chain rule? The derivative of the outside function, which this thing is being squared, I drag down the 2, and then I subtracted 1 from the exponent, and then I have to multiply whatever the derivative of the inside is, which is 1. It should have been negative 1. Whoa, okay. So very, very tricky. So this should have been, let's see, and oh, and then here I made a mistake. So I'm making lots of mistakes, guys. The last statement here was negative x times negative x. That should have been plus x squared. So if we found the derivative of this should have been 0 minus 40. So that should have been 0. The derivative of minus 40x is minus 40, and the derivative of x squared is 2x. Let's see what we have down here. If we multiplied this whole thing by negative 1, this should have been minus 40 plus 2x. Pick your poison. Pick the way that you like it, because you can kind of see from my example, either way you can make mistakes, okay? But both ways will work, okay? So you should have, let's see. And I do apologize. God, I'm making mistakes left and right. This should have been 2x. So I'm so sorry about that. That should have been 2x. I don't know what I'm doing here. So I have 4x minus 40. Not bad. Okay, so that should have been just the first derivative. I do apologize that became so much more difficult than it needed to be. The next step is to find the critical points. So that means wherever the slope is equal to 0. So this was the slope or the derivative. We set that equal to 0. Kind of works out nice. Okay, so I found the critical value is equal to 10. Then I draw a number line. And just remember from the last problem, there are endpoints of 0 and 10 or 20 because, again, the condition was simply two numbers. They have to be non-negative and their sum is 20. Two numbers, both of these are numbers that if you add up, they're going to be up to 20. If you don't believe me, add them. Literally add them. I should have done this in the first step, but this would just be 20. Kind of mind-blowing, isn't it? Okay, but that does follow the rule. Their sum is literally 20, okay? I know it's kind of weird, but it does work out, right? Everything kind of works out if you think about it. If you do it correctly and you set it up correctly, okay? And the endpoints have to be 0 and 20 because they have to be non-negative, so it can't be any negative numbers, so that has to be the endpoint, 0. And then because you set that first parameter of 0 being the endpoint, the other number can't be anything greater than 20. So that's why we have endpoints of 0 and 20. Okay, wow, this looks very familiar again, but let's double check and see. So okay. Okay, so let's find, I'm going to use x equals 1. It's a little clue here. I'm going to use x equals 1, plug it into the first derivative. So that should be 4 times 1 minus 40. That is negative 36. That's a negative number. Let's try 12 again. X equals 12. So I'll do f prime of 12 is equal to 4 times 12 minus 40. That's going to give me, let's see, positive 8. That will, if you remember anything here, what is it? Any functions that have negative slopes going to your 0. So in this case, at x equals 10, that slope is 0. And then after that, it's positive slopes. That's a minimum point. I don't want that. So that's actually, this time, this is a local min. I don't want that. I want maximum points. So that's not going to work. So that's why we set up the actual endpoints, because we can test to see if the endpoints are significant as well. Let's try this out. Let's try a number that's greater than 20. Okay, I guess it really doesn't matter. You can say x equals whatever you're comfortable with. I say 21. You could say 30, 40. Well, I don't know. However you like it. F prime of 21 is equal to 4 times 21 minus 40. let's see, that should be... That should be, sorry, I'm doing the math in my head right now and seeing where this is going to go. That should be 44, so that's still positive. Huh. If I plugged it into here, let's do numbers that are less than... Okay, that's odd, but okay, so let's see, less than 0. So let's just do x equals -1. That should give me f prime of -1 is equal to 4 times -1 minus 40. That's still negative, huh? Sorry, guys. Give me 1 second. I'm still trying to figure this out. Alright guys, I'm gonna have to stop this video to see what's going on. Yeah, this doesn't quite make sense to me, because these were supposed to be the endpoints, 0 and 20, so I do apologize for taking up your time. Alright guys, I guess I'll have to see you in the next video. It kind of bums me out a little bit.